Kalyan, and I'll be sharing my takeaways from this paper, Method Overloading the Circuit. I did start preparing slides, but I thought I would try this format of actually walking through the paper itself with main takeaways, main observations, and also switching to some other reference material in the beginning, in the middle. So let's see if this approach works out. If not, I can always switch back to the slides in a future forum. So I'll get started. So the main thing here for this main takeaway from this paper, first of all, I really enjoyed reading this paper. It's really well written. And if you haven't read it yet, I would highly encourage reading it. I got a lot of learnings from it. So the main thing the authors talk about here is first about, hey, there is the whole evolution of microservice architectures everywhere in various, like it becoming the most common form of building distributed applications. And with microservice applications, while we are trading off the technical complexity, right? Like an individual team or a developer doesn't need to know the whole system. At the same time, it introduces different challenges. For example, one of the challenges is the need to handle partial failures. So for example, let's say you have a Netflix application, and maybe it is talking to different microservices. Maybe one is giving you the items from your watch list, one is probably giving the list of trending movies and whatnot, right? Like so many different aspects of the application. What is as a developer of that application, now I have to know, hey, what is my fault tolerance behavior, right? What if the bookmarks service or my watch list service is unavailable? How does my application handle it gracefully and degrade gracefully? So they talk about just to give the overall flow of the outlay. They talk about microservice applications. They talk about the need for fault tolerance and the need to handle partial failures, and then different fault tolerance techniques, right? Overall, like things like timeouts, retries, circuit breakers, load shedding, etc., to improve the overall reliability of the system. And then they talk about go deeper into circuit breakers itself, what they are, and what are some of the problems today, and they have not been studied as deeply in the industry and in the academic world. And this is basically a step in that direction of, hey, how does application design impact circuit breakers? And a lot of things we do to minimize like duplication in applications or to improve code reuse can actually be counterintuitive in terms of how the sensitivity of the circuit breaker installed there. So they talk about the relationship between the abstractions used in applications, how they affect circuit breakers. And then they go on to propose 2 new circuit breaker designs. And they talk a lot about the different properties we should know about and the right scoping and all of that. So I will share my observations. And a lot of these are based on the observations at DoorDash. So there are 2 very good case studies, and we will go more into that. Cool. So let me start with, and please feel free to interrupt me at any time, and we can just have the conversation if something is not clear. So to start with, so the partial failures, right? The microservice applications, the complexity where now as application developers, they have to know about how do I handle failures? What if this dependency that I'm depending on is either unavailable or taking a lot of time or returning failures, etc., right? So a common way to handle this or to understand this is by using fault injection techniques to identify the issues in application code. Hey, is my application code handling this dependency not being available or it taking a lot of time, etc., right? And using that fault injection techniques, you can now say, hey, these are all the specific areas in my application where I need to improve the fault tolerance. And then you use the right fault tolerance techniques. It could be like, hey, I have the right dosage of retries, or I have the right circuit breakers installed. And each of these fault tolerance techniques serves a different need. So that is basically the first outline in terms of first identifying the areas in the application that are vulnerable to these dependencies not being available, and then going and applying the right fault tolerance techniques. And the authors also have a system called filibuster, which is a way to do this fault injection testing. So I'll just bring it up. So it's called filibuster.cloud. So there's actually a separate paper on filibuster, which is kind of from this, at least one of the authors is the same. And I haven't read that paper fully, but basically this talks about how to do this kind of fault injection testing. So now, okay, you've done the fault injection technique, you have the fault tolerance techniques. And the goal of the fault tolerance, improving the fault tolerance is, hey, I want to make sure my application can both tolerate and react to both non-fatal and fatal errors of service dependencies, right? But the authors claim that, hey, this is not happening at a granular level today, right? It's very primitive. So what they're saying is, hey, maybe if an entire service is having a failure, that's a different story. But let's say only one part of the service is having a failure, but the fault tolerance could be too coarse that it prevents me from talking to that service just because one method in that service happens to have a problem. So DoorDash has a few examples. I will when I come to the case studies, I'll talk about what this really means. So that's the overall outlay of the thing. And then let's go into circuit breakers itself, right? Circuit breakers is one of the fault tolerance techniques where you want to say that, hey, I'm talking to a downstream system, some dependency, and let's say that dependency is having a problem, right? Maybe there's a buggy deployment, or maybe it is having a bad time, it's completely overloaded, not really returning back, doing anything useful for me. So instead of bombarding it with more requests, circuit breakers are a way to give that downstream system a break and basically say that, hey, like there's no point in just continuing to fail. So once my failures cross a particular threshold during a particular sliding window, the circuit breaker is basically going to short circuit that RPC invocation, and it's going to say, yep, the circuit is open now, calls don't go to that service. So it basically helps improve the overall reliability of the system, because number one, you're not keeping on making requests to an already overloaded or a system that's failing and inducing some kind of metastable failure. And you're also keeping the calling application sane by short circuiting it and not really making those calls which are going to be highly probable that they fail, right? So that is the primary pattern of circuit breaker. And circuit breakers have this kind of, you can think of it as a state machine, where initially the circuit starts off in the closed state, and basically the circuit breaker is something that interposes itself between our RPC invocations, right? And so let's say A is calling B, and there is a circuit breaker associated with A. And now that circuit breaker is observing the responses from B. It is saying, hey, here is what is the error rate, here is the response times, etc. And then during a particular sliding window, if the failure threshold is exceeded, then the circuit breaker, the state switches to an open state. When it's in the open state, it's not letting any calls go through. And at this time, you can imagine there is like some kind of a timer starting based on what you configure the circuit breaker. So let's say that's 1 minute. And after that delay, the circuit breaker switches into a half open state where it's kind of in a trial mode. It's going to now try like one request and see, is it succeeding? If it succeeds, it goes back into the original starting state, closed state. If that fails, it comes back into the open state. And this is basically the state machine. So the authors talk about that as well. So now let me go into the main parts of the paper, which is the taxonomy. So they talk about the taxonomy of circuit breakers. So they have looked at a lot of circuit breakers across libraries across many open source systems. And the main thing here is, the way the circuit breaker is installed, right? So you can either do it at the application layer or in the infrastructure layer. So the main first, you can think of this as multiple forks in the road. First decision you want to do is my circuit breaker is in some kind of like a service mesh kind of a system, say like Istio that supports circuit breakers. So basically, as an application developer, I'm kind of getting it for free. Like I have not written any code, but I'm just using some kind of a proxy service that is interposing itself between my application and some other downstream system to which I'm making RPCs. And then that infrastructure layer, that proxy service, is acting as a circuit breaker for me. That is one method, right? The other one could be in the application itself. You're not using that external proxy service, but within the application, you're doing the circuit breaker. But now you have the other decision or the other thing within the application. Is it explicit or is it transparent? So is it that do you see that right and center in the code as a developer, or is it kind of happening behind the scenes for you, right? Like where, let's say you're calling some other maybe there is some kind of auto instrumentation, or maybe there is some kind of a library you're using, RPC library, which whenever it returns an RPC client, automatically attaches a circuit breaker to it, and you don't really, as a developer, go and explicitly do anything, right? So that's the second part. If it's an application level, is it explicit or transparent? And then here within explicit, you can again have, where do you install that circuit breaker? So you have three options here. One is the call site. When you say call site, it's wherever that RPC invocation is happening, there the circuit breaker is attached to that call, to that RPC invocation. That is the call site explicit. So I'll just show a very quick example here. So this is like an example of a call site explicit circuit breaker, where let's say there is some service which is calling some other service here, like some RPC method, but it has installed this circuit breaker policy, which it was initialized somewhere here, to say that I can handle at most one exception, and my delay time is 1 minute for it to go back into the half open state. So you can see that this is an example of a call site explicit circuit breaker, because this is the place at which this RPC call is being made, and it is being wrapped around with this circuit breaker policy. So before this call happens, it's going to check the state of the circuit to see if it is open or closed. And only if it is closed, it's going to allow this call, right? So that is the call site explicit. And then there is method explicit, where there is a method which is making the RPC call, and you can go and do some annotations on that method to say that this is the exception type that needs to be handled to update the state of the circuit breaker. And then there is a client explicit circuit breaker, which is directly on the RPC client or the HTTP client by adding some kind of a decorator on the on that client. An example of that could be something like this, where you're building some HTTP client object, and then you attach a circuit breaker along with it. So the reasons these are all important is they affect the scoping and the sensitivity, which we will go into. So those are the three types, right? So within explicit. But then when it comes to transparent, there's only one type, which is the client transparent circuit breaker, which is that it's very similar to this client explicit, except that it happens without the application developer attaching that circuit breaker along with the RPC client, but just assume that they call some RPC library, and then that automatically returns back an RPC client with this circuit breaker attached to it. So that is the quick taxonomy. Now, so we saw two things, right? So we saw where the circuit breaker is associated with. Is it at the calling place, at the method level, or at the client? And then we saw the transparency, which is explicit or transparent, right? Those are the two things we saw till now. Now, based on these two, this is the most important thing from this paper, which is sensitivity. Now, you have some application code. You have now created some circuit breaker for these to handle the RPC invocations or HTTP invocations to some other downstream system. But what is the sensitivity of that circuit breaker? So what this really means is, if I have a circuit breaker, let's say I have attached it with an RPC client, And let's say that RPC service has, like, say, 10 different RPC methods that are exposed. Now, if I use that RPC client to make a call to the same RPC client, but I'm using it to make any of those 10 different calls, and let's say only one of them has a problem, and that's going to affect the circuit breaker state. And even the other 9 endpoints which didn't have a problem are going to be bound by that same circuit breaker's state, right? So even though that one single method had a problem, now I'm going to be blocking any kind of invocations to the remaining 9 methods. So here we can say that the sensitivity is low, right? Because its circuit breaker is just sensitive to the invoked service, not to the specific RPC method or to the arguments. And the next level of increasing the sensitivity would be, hey, my circuit breaker is sensitive to the RPC method also. So for example, if only one of those 10 methods is failing and say overloaded or whatever reason it's failing, and the circuit breaker state is separate for each of those 10 methods. So it is more, it's considered more sensitive. The sensitivity has increased. But then within that method, let's say only one type of argument causes a problem, then it is still not fully sensitive, right? It is still, I think as I explained the first case study, that thing will become clearer. But this is actually one of the main things, like sensitivity, and how do you increase the sensitivity is one of the main things the paper talks about. I'll pause here to see if there are any questions so far, and anything that is unclear so far that I can try to clarify.
So what is the caller's behavior when the circuit breaker is open? It's not letting any calls through. Do the calls queue up or do they get dropped? What exactly happens?
So what would typically happen is it's like through the circuit breaker. I think it probably depends on the specific library. But if I take this example here, if I take this example of the Poly library, which is kind of like the de facto circuit breaker library in .NET, the behavior is that it would throw any calls will fail with a broken circuit exception. So as a client, you have to handle that exception and say you try to make that RPC call, and then it will just, the circuit breaker state, if it's open, it will just give you this.
Okay, thank you.
Okay, cool. So sensitivity, let's take a concrete example that will make this clearer. So these are 2 case studies from DoorDash. So DoorDash has obviously an orders service where you can place orders, modify orders, cancel orders, etc. So this is kind of a simplified version of the orders service. So here you can see there are 3 methods, right? So imagine this is a order service, and it has like these 3 RPC methods: create, order, modify an order, and then cancel an order. So, and they make a call to another service called an auth service, which is supposed to handle the payment associated with the order. I don't know why it's called the auth service and not the payment service, but that doesn't matter for this example. But the overall idea here is I have an order service. It's making a call to another service which handles some payment related aspects. So let's say you started off with this initial code, and then you say, hey, like all of my methods, the create method and modify method, delete or cancel order, I'm having this repeated RPC calling code to that auth service. And so you say, oh, I'm just going to refactor this, right? Because we like code reuse. And we say, okay, I'm going to just refactor that into this issue auth RPC. And that RPC invoking logic goes inside that common method. And then I just call issue auth RPC here. So this is like the flow I'm just explaining to introduce the bug or the challenge with circuit breakers. So, and then you call, you just say, okay, what is this for, right? Because auth service or the other service that we are calling also has 3 methods for order, like the payment related activity for create, modify, and delete. So that just becomes a parameter here. So this call that goes to the auth service goes on that corresponding method, create, update, delete. And so now, now let's say you want to attach a circuit breaker with this, right? So I talked about this method explicit circuit breakers, where you can annotate a method depending on what library, open source library is used. They could have different mechanisms. This is an example where this method is annotated saying, hey, I want a circuit breaker to be associated with this. So before this method is actually executing, examine the state of the circuit breaker and make sure it is in a closed state, etc., etc. And this is the expected exception from that invocation that should increment the state of the failed counters and all of that, right? So the problem, or there are two problems with this approach, as the authors call out. The first problem is that this RPC exception, we are kind of reusing the same method to issue those 3 different RPC methods, right? To the auth service, it could be the create method or the update method or delete method. And they all might be different, throwing different types of exceptions, which we are not really handling. We're just trying to handle everything as a same, which can lead to incorrect behavior. And also with gRPC, it may be like specific error codes, which we may have to ignore. For example, there may be the non-fatal errors, like say maybe like a resource not found or something like that. So that should not really affect the state of the circuit breaker. So this is 2 cores. That's one problem. The second more important problem is, let's say there's a bug that affects only the cancellation of orders. Let's say the bug is, hey, when I try to cancel a DoorDash order, I'm not able to properly refund or the whatever that auth service has to do, right, for the payment work. Let's say that it's not able to do properly. But the way the circuit breaker is installed, it will affect even creation of new orders and also modification of existing orders. It's not just affecting the cancellation. So that's the main takeaway here. Main takeaway is you need the proper sensitivity associated with the circuit breaker. So you would ideally want something like a separate method that takes care of doing the call to the auth service for the create order, separate method for delete order, separate method for update order. And then the other takeaway is you want the specific exception types associated with that create functionality, maybe that it has specific exceptions that needs to be handled. So in this case, what's happening is we are kind of trading off some of the code reuse and all of that. Now you have to have these separate methods. And now in the order creation, even though you're calling the same auth service and this part looks exactly the same, it has to be duplicated so that you can attach the circuit breakers at the right scope for each of them. So the authors call this as partitioning. So 2 things they call about. One is partitioning. To increase sensitivity, developers must refactor code to partition RPC invocations that need separate circuit breaking. Fairly straightforward, because if I want my order cancellation errors to be treated to not affect order creation, I would need to have this partitioning. And then the second related takeaway is how you do this partitioning is dependent on how you have created the circuit breaker. For example, if you have done the method-based circuit breaker, like what this example has, then you do it, then you partition by method. If you ended up with the client explicit circuit breaker, then you partition by client, right? For example, you may use different RPC clients for each, with its own circuit breakers for each of the calls to the different endpoints. So this is basically insight number 1. Partition, first do the correct partitioning so that you have the right sensitivity. Insight number 2 is how to do that partitioning. Do it depending on what scope you ended up with. You ended up with method-based, you do the partitioning by the method-based. Any questions so far before we go to case study number 2? Was this straightforward, or is it any aspects of this that I can help clarify? Okay, I'll proceed. Yeah, if any questions, please feel free to interrupt. So the second case is just an extension of the first case. And so they have the same order service, but they want to introduce a new order type called, so let's say initially it supported only delivery orders, right? You place an order, things get delivered to you. Now they want to say, okay, I want to support takeout orders in addition to delivery orders. Now there are a few possible ways by which you can support both delivery and takeout. And even though this looks complicated, the basic idea is very simple. So what they're saying is you can parameterize this in different ways. So for example, you can say, hey, I will have separate. So imagine, so remember there are two services, right? There is the main order service, and then there is the auth service, which is handling the payments. So in the main auth service is the invoking service, and the payment service or the auth service is the invoke service. So you can have these 6 combinations where you can say, hey, I will have separate methods, RPC methods in my main invoking service. I will have a separate one for takeout order cancellation, delivery order cancellation. Like let's zoom in only into cancel, right? Forget about create and modify for now. But within cancel, I will have separate RPC endpoints for takeout order cancellation and delivery order cancellation. And that's by invoking method. I have a takeout cancel and delivery cancel are separate methods. And then I will have a separate auth service specifically for the order type. I created a separate takeout auth service that handles takeout orders, creation, deletion, cancellation, right? So there's a takeout auth service. So if I have this thing, what I can do is I will create this separate method. And whenever the takeout order has to be canceled, it will land in this endpoint. And then this will call the payment service specifically created for the takeout order type, and call that one and say, go delete this order. That is one option. The other option is we could say, I will have a separate order cancellation for takeouts, separate order cancellation RPC endpoint, but I don't want to duplicate that auth service. I'll have the same auth service. I'll just have a different method on it that says takeout delete, and there'll be a separate method for the delivery delete. And that's basically by invoking method and invoked method. So basically you're designing your application this way. Or the third option is you could say, hey, I will have the same, I will have a separate method in my original service, the order service, but in the other service, in the auth service, I have the same auth service and then the same method in it, but I'll just pass a parameter or an argument that says whether it is the takeout order or a delivery order. So these 3 are like one bucket, right? Where you have decided to use a separate RPC method for different order types. And then whether you duplicate the other service or you only duplicate the method, or you just pass different argument. That is one flow. These 3 are similar. You can, here you have decided not to duplicate your RPC method. You just have one order cancellation method, but you take a type. Hey, is it a takeout order being canceled or a delivery order being canceled? And then the same 3 decision points. Do I duplicate the auth service? Do I just duplicate the method on it, or just duplicate the, not duplicate anything, but just have the arguments for it? So most developers will choose this option in the spirit of like not having to duplicate functionality, code reuse, etc. So you'll just say, oh, new order type I have to support, no problem. I already have an order cancellation. I'll take an order type, and I already have this auth service, which already has a cancellation or delete method. I'll just send it an argument which says whether it's a takeout order or a cancellation order. So the authors argue that, hey, this is what they end up using at DoorDash, but this is the one which is most tricky from the circuit breaker design. Because now how do you, because one of the bugs they had in DoorDash, like a real bug, was only the cancellation of the takeout orders was having a problem. But because of the sensitivity of the circuit breaker not being configured correctly, the cancellation of all orders was broken, right? Because ideally you would want only the part which is having the problem to the circuit breaker to affect only that, right? So this is where the whole sensitivity comes in. So here you can see this is very tricky because from a code reuse perspective, there's a tension here, right? Because you want from a general abstraction perspective to have something like this, but then how do you really associate the circuit breakers in a way that you get the benefits of like the correct sensitivity and also the ability of one thing failing to not affect other things. So all of this is basically the explanation for what I just mentioned here. So the main things they talk about here is something called the path sensitivity, right? So now you want ideally you want if only the cancellation for let's say that payment cancellation only for takeout is having a problem, you want it to affect only that and not affect payment cancellation for the other order type delivery. So in some cases, depending on which approach you take between these 6 possible approaches, here, for example, if you take 1B here, we have the invoking method, which is separate, but then the invoked method, let's say you have a circuit breaker here, right? So now this has to be sensitive to the path, like is it takeout / delete or delivery / delete? So that's the whole path sensitivity concept. And then if you have something like this, it has to be actually sensitive to even the arguments, the RPC arguments. It has to be ideally say that because everything is the same method, right? And whether it's a takeout order or delivery order, you're going through the same method. So it has to know that based on the arguments, my calls to the cancel for the takeout cancellation have been having a problem. So I have a separate circuit breaker state. And then for the delivery orders, they have been not having been a problem. So that circuit breaker state should be separate. So they talk about 2 things. One is path sensitivity and the other one is context sensitivity. So circuit breakers aware of the invocation path improve the sensitivity of circuit breaking. That is one part. And then context sensitivity is a more trickier one. The circuit breaker is even aware of the invoking RPC's arguments to further improve the sensitivity of circuit breaking. Any questions so far? Okay, so I'll continue a little bit more. So now they talk about some of the implications of all of this, and I think kind of generalizing from these case studies, and how do you really give guidance to application developers, right, in terms of what they should do. So the second part of the remaining part of the paper focuses on the guidance and some more challenges with respect to this. So I'll take one example here. Again, this is from one of the paper authors. There's a good video which talks about a short video that talks about some of the main takeaways from the paper. So we saw this basic example, path sensitivity, context sensitivity. This can be even more trickier. Let's take this example. So let's say you have 4 services, service A, B, C, D, and let's say you had forget the E for now. And let's say you had a circuit breaker installed at C for calls going to D. Now, let's say one day this new service E got introduced, which is starting to make calls to service C. And now service A also starts calling service E. And let's say that for some reason, the way the parameters or arguments are sent, etc. So any calls originating from E, let's say that is triggering some faults in D. But this flow is not triggering faults in D. So, but the circuit breaker is shared between both flows, right? Whether it comes from AEC or ABC, it's the same circuit breaker for call going from C to D. So that can be problematic because now even though only this flow is affecting the state of the circuit breaker, even the other flow would get affected. So that's an example of how if you don't have a path sensitive circuit breaker available to use, then you may have to refactor it into two different methods. Depending on the flow, you may have to say, hey, I really don't want this flow to affect my other flow. So you would have to break it down into two separate RPC invoking methods, kind of similar to the partitioning concept. And then there's another example here, which is about context sensitivity. Again, here the example is you have these 4 services, and then there is a new canary service of D. And this is being, let's say this is like a new version of the service being tested, and there is like some kind of traffic going here. But let's say this new service version has a bug, and but the circuit breaker, if it is shared, now you're going to impact both flows, both calls. So the paper goes more into the implications of this, and one of the things it is proposing is something called distributed execution indexing, and this is there's actually a separate paper on this, and I kind of ran out of time to read that paper. But the way I took it as the main idea here is it is kind of encoding the RPC invocations by generating some unique identifiers, encoding the path taken by RPCs, so that circuit breakers that need to be very path sensitive can understand which path is being taken by the request, and can have different states for different requests. So, but that's something I plan to read up more. And they also talk about how it integrates with OpenTelemetry distributed tracing framework. But this seems like at least the paper I looked it up, it seems like a work in progress paper. It's not yet fully published, so it's still very new. That was my interpretation. So overall, what the paper recommends is use path sensitivity as much as possible, because context sensitivity based on the arguments is more tricky, because you can't just say which arguments to be used, right? Because let's say this order type, we wanted to do circuit breaking on order type, but not on, say, user ID or order ID or other things, right? So how you have to be really precise on, this is my partitioning for which arguments matter for context sensitivity and which ones don't matter. So in general, they say, hey, go make sure it's path sensitive, like different, like refactor appropriately to make sure that you have path sensitivity. But context sensitivity is only when you have to retrofit into existing applications that you don't have the luxury of refactoring. So, and then these are kind of generalizations of the flow. I talked about those 3 things, like service, path, and context. Those 6 combinations. This is basically taking it forward as a decision tree. So I think this is the main takeaway. Path sensitivity meets a sweet spot with proper sensitivity when the application is designed accordingly. So. Yeah, I think one last thing I'll mention here, which one interesting thing here is they gave this example of a bot that was crawling the website. I think I assume it was the DoorDash service. And the bot was issuing malformed HTTP requests. And because of this, one of the internal services, many levels deep, started returning a HTTP 400 bad request. And some other higher level service remapped that into a 500 internal server error. And so what happened is, because of this bot issuing this malformed HTTP request, the circuit breakers started kicking in. And so the regular usage was also affected. So this is an example the paper gives of how some one request originating outside of the common use ended up decreasing the reliability of the system. So this is again another kind of data point in terms of configuration of circuit breakers and how it can affect. Another interesting example, I'll probably stop with this one, is misconfiguration of circuit breakers. So they give an example of a fan out example. So service A is doing a fan out to B, C, D, E. But what was happening is one of these services, say B, is returning failures. But then the calls to C, D, E, they were cancelled. But since the circuit breaker was not really differentiating between the cancellation exception and the regular exception, it ended up blocking the communication from A to C, D, E, even though C, D, E didn't have any other problems by itself. It's just because of the way the programming language with coroutines and all that was set up, it ended up being blocking the communication between these other services which didn't have a problem. So the main takeaway is like, hey, how do you place the service circuit breakers? How do you configure it? This needs more research and more guidance to developers because of all these interesting things. So ideally, it should have ignored the cancellation exceptions and not counted them as errors between these two. So I'll just do a quick recap. So the paper examined use of circuit breakers in DoorDash and in general, many open source libraries. And the main thing they talk about is how the application design or whatever abstractions we use to make applications have better code reuse, reduce code duplication, etc. How do they end up influencing how the sensitivity, right? What's the sensitivity of circuit breakers? How do they influence that? So those two case studies we looked at, one case study was the first one for where the wrong scope, instead of circuit breakers for create, delete, and modify, if they shared the same circuit breaker, just because there is a bug in the delete, it ends up affecting both create and modify. That was one case study. Second case study was the takeout order and delivery order, and cancellation of the takeout order. If it has a bug, it should not end up affecting the cancellation of the delivery orders or any other operations. So that is the other example we saw. And then we looked at path sensitivity and context sensitivity, and how the circuit breakers should ideally be designed for path sensitivity so that you have the right partitioning in place. So that's pretty much my takeaways from this paper. Hope this was useful, and I think we can now open it up for Q&A, right?